Hello, good morning, good afternoon, and good evening to everyone who's tuning in. Hope you're doing well and staying safe. On behalf of Biopetro Arab Oil and Gas Academy, Arab Guru, I would like to welcome you all in our last session in the course Introduction of Well Control. I'm Mayartar, senior year gas and petrochemical engineer student at Alexandria University, and I'll be your moderator for today. Please don't forget to drop your questions in the Q&A section below and to keep the chat box professional and ethical. And don't forget to submit your quizzes because it's the last session. And without further ado, let us give a warm welcome to Dr. Hussein Emadi. Dr. Hussein Emadi joined Bob L. Department of Petroleum Engineering at Texas Tech University in 2014 right after completing his PhD study in petroleum engineering at Texas Tech University. Prior to Texas Tech, Dr. Emadi worked as drilling engineer at wellsite drilling engineer with Apache and Petroparas, a national Iranian oil company in the United States and the Middle East. His research and over a decade of professional experience include a focus on wellbore integrity, artificial intelligence, subsurface hydrogen storage, rock mechanics, and artificial lift. Up to now, Dr. Hussein graduated 5 PhD students and is advising 2 PhD candidates. Additionally, he graduated 1 master's student and is advising 2 master's students. Dr. Hussein has authored and co-authored 55 technical papers. He also co-authored one book chapter in Fracturing Horizontal Wells book. He also filed 2 U.S. patents so far. Dr. Emadi serves as the faculty advisor for Texas Tech University, American Rock Mechanics Association. Dr. Hussein is a member of the Society of Petroleum Engineers and the National Society of Professional Engineers. Thank you so much, Dr. Hussein, for coming today, and the mic is yours.
Thank you, Maya, for the introduction. So this is the last lecture on the introduction to well control. I think the last session was 3 weeks ago, and I was talking about the two well killing methods, the weight and weight and drillers method, and how the pressure gauges on both casing pressure and standpipe pressure behave during the circulation. And in this slide, you guys see how uh, the pit gain, the pit level, mud pit level changes when we circulate out the gas. As you can see here, we see uh, here we see increase. And this is due to the gas expansion. And when the gas reaches the surface, we see the maximum pit gain because of the expansion which we allow to happen to reduce the pressure inside the gas bubble. We see the highest pit gain, and after that, since we're replacing the gas at the surface with the mud, so the level of the gas in the pit starts to drop, and it goes back to uh, zero basically because at the end of the circulation, the entire annulus and drilling will be filled with mud. Uh, if the previous slide and the previous slides were about when the formation fluid is gas, however, when the formation fluid, for example, is salt water or oil, the behavior of the casing pressure is different because because unlike gas, which is highly compressible, salt water and oil, we treat them as incompressible. What happens when a kick happens and the formation fluid is salt water, uh, and we obviously implementing weight and weight method, as you can see here, since again liquid does not expand. When we start pumping the kill mud, as long as the kill mud is still inside the drill string, you see the first part, this part, casing pressure remains constant because casing pressure basically uh, tells us the difference between the bottom wall pressure and hydrostatic pressure inside the annulus, and this is casing pressure. And since nothing is changing inside the annulus, and the assumption to perform weight and bait and driller's method is constant bottom wall pressure, so casing pressure remains constant. However, when the kill mud starts entering the annular section of the wellbore, hydrostatic pressure inside the annulus starts to increase. So when this one starts to increase, the difference starts to decrease. So we see the second part, which is decrease inside the decrease at casing pressure. And basically the slope will be a function of the difference between the kill mud weight density and current mud density. When the formation fluid, which is salt water in this case, reaches the surface, uh, now we are replacing uh, salt water with the kill mud, and kill since the difference between the density of the kill mud and the salt water is higher than the, the, the difference between the kill mud and current mud. So you see a steeper um slope here. And at the end, when the salt water is completely out of the wellbore, we are replacing the current mud with the kill mud. And at the end, since the entire uh, drill string and annulus gets replaced by kill mud, the well basically is killed, and we don't see the effect of the bottom wall pressure, which is formation pressure at the surface. So we're not, we shouldn't be reading any pressure. However, in reality, after killing, we should see some pressure because of the thermal expansion. The question that may come to our mind after talking about both methods, weight and driller's method, which method is preferred one? Obviously, this depends. This depends on time required, surface pressure, ease of implementation, and fracture propagation pressure of the weak formation. Time required meaning that, let's say, if we have the uh, additives, weighting agents like barite ready on rig location, and we can prepare the kill mud fast, obviously we go with the weight, because uh, if you guys remember from the let me go back to so this is Driller's method. As you can see here on the x-axis, we see the total number of strokes required to implement Driller's method. As you can see here, we need almost 13,000, 14,000 strokes. Uh, However, if we want to uh, implement weight method, it goes down from 13, 14,000 down to a little bit over 7,000, let's say 7,300. So basically, it requires one circulation, so less time to implement the method. However, sometimes we do not have the uh, the weighting agent unlocate at the location. So we go with the Drillers method. Surface pressure. When we are dealing with gas, if you guys remember from the previous lectures, uh, handling gas is way more challenging than handling salt water and oil because of the compressibility of the gas. And remember, we always let the gas expand, because if we don't let gas expand, what happens? The pressure inside the gas bubble doesn't change, and we see the reservoir pressure at the surface, which is not desirable. Uh, Surface pressure, what surface pressure we are expecting, ease of implementation. Sometimes you know that it's uh, it's quicker to kill the wall using weight and weight method. However, the drilling personnel is more comfortable implementing uh, weight and weight, driller's method. In this situation, despite the fact that weight and weight method is faster, because we want to always make sure that we do and complete the operation in a safe manner, because always safety comes first. We implement driller's method, and also fracture propagation of weak formation. We know that during killing operation, one of the one of the items we need to keep in mind is making sure that no casing burst or no surface facility damage or BOP damage uh, occurs in the cases whole system and at the surface. And also we do not fracture the weakest formation, which is presumably located right below the previous casing shoe. So we need to know the fracture propagation of that formation, and we need to make sure that the surface pressure does not exceed certain value mass that fracture the weak formation. So so far I talked about two different well killing methods: driller's method and weight and weight method. There is another method which is not a killing method, uh, and we need to implement that method or that technique when we do not have uh, for some reason we don't have the ability to pump, or sometimes uh, we are tripping out. At the middle of tripping, we see that formation fluid is entering the wellbore, let's say because of swapping, for or if the bit nozzle the bit nozzles are clogged, so uh, we cannot have circulation. We call that volumetric method. So volumetric method is basically removing gas influx when any of these issues happen. For example, if you're, as I previously mentioned, we are tripping out of the wellbore and we are not off bottom. So after a while, we notice that formation fluid is entering the wellbore. Obviously, this is not a kill method. Why? Because the entire objective, the whole objective of this method is to circulate out the influx, which is gas. Because if the formation fluid is oil or salt water, we don't need to implement this method, because we need to have a forced circulation. However, when we have gas, and gas, let's say 1 gallon of gas enters the wellbore, it causes way more problems than salt water. How? In this way: when 1 gallon of salt water enters the wellbore, a downhole condition, it stays there. Or if it moves due to the density difference, it moves very slowly. And since it's incompressible, the volume does not change. So 1 gallon salt water at the bottom of the wellbore will be roughly equal to 1 gallon right at the surface. However, if 1 gallon of gas enters the wellbore, depending on the pressure of the formation that gas is entering the wellbore from, the volume increases because as the gas moves upward and the hydrostatic pressure acting on the gas bubble starts to decrease, the volume of the gas starts to increase, provided that it's isothermal condition. So hydrostatic pressure, which is acting on the gas bubble decreases, the volume must increase. P1, V1 equals to P2, V2. So if we look at this, the Boyle's law here, we had this in previous slide too, but just to make sure that everything is clear. For example, if we have, let's say, 5 gallons of gas entering at the wellbore at 10,000 or 8,000 psi, when it reaches the surface, it becomes 150 gallons. And when the gas bubble expands, obviously it pushes out the drilling mud inside the annulus, and we go even more under balance. So more formation fluid, which is gas, can enter the wellbore. To prevent that from happening, or to prevent getting blowout, let's say uh, this happens during tripping out. We know that we were overbalanced, and the only reason uh, gas bubble entered the wellbore uh, is because of swabbing, meaning that the bottom hole pressure dropped below formation pressure, not because hydrostatic pressure of the gas column was lower than formation pressure, because we were tripping out too fast. So if we can replace the gas with the mud, with the current mud, we shouldn't have any issue, meaning that we can go from underbalanced condition again back to overbalanced condition. So the main point, the main objective of this method, which is volumetric method, is to bring out the gas bubble in a controlled manner up to the surface and then replace the volume of the gas with the current mud. Why? Because by replacing the gas bubble with the current mud, we should be fine. When if the kick happens due to fast tripping. If kick is happening because the mud weight is not sufficient enough, we can do some calculation and calculate the kill mud and replace the gas with the heavier mud. So basically, it is very similar to the first circulation of the driller's method. However, it is not a continuous circulation. It's basically it's intermittent approach. So we let the gas expand and then replace it with then remove the mud and then expand, remove the mud volume. I'll talk about the exact calculation in future slide. So basically, gas influx is brought up to the surface by means of migration and controlled expansion. Casing pressure keeps increasing, similar to Driller's method, first circulation. Casing pressure keeps increasing, but instead of a continuous increase, you see increase, remaining constant, increase, remaining constant, increase, remaining constant. And obviously, bottom hole pressure remains constant by bleeding off, calculate the volume of mud at the surface. If you guys remember from the previous lectures, in both weight and weight and driller's method, the assumption is we are doing the circulation by maintaining the bottom wall pressure constant. So the bottom wall pressure is constant, and it has to be always more than formation pressure, because otherwise more uh, formation fluid can enter the wall. So what happens is, if you guys remember, when when gas enters the wellbore, if we don't do anything, gas starts moving upward. And due to the gas migration, we see increase at the surface pressure, which is casing pressure. So we have to determine the pressure increment, and then we calculate the volume of the mud we need to remove equal to the pressure increment. And by repeating this, we can safely bring the gas bubble up to the surface and then replace it with the drilling mud. So uh, by doing that, and once the gas influx reaches the surface, what we do, we calculated the volume of the gas at the surface, and a calculated volume of the same or heavy mud is injected to the annulus through the kill line, and uh, and the well basically gets killed. Uh, and like the driller's method, casing pressure keeps increasing. Again, not continuously, uh, sporadically. And how we maintain the bottom wall pressure constant by bleeding, uh, calculate the volume of mud. And bottom wall pressure always above formation pressure. So let's look at the casing pressure, hydrostatic pressure inside the annulus, and also bottom wall pressure as we implement volumetric method. So when we start, when a when gas enters the wellbore and we are off bottom, and it happens, let's say, because of fast tripping, as soon as we notice that, obviously we close the BOP. So we close the BOP and we start monitoring the pressure. And let's say it's 500 psi. Since we want to always be overbalanced, and as a safety factor, let's say we assume safety factor equals to 200. So we wait till casing pressure increases by 200 psi, and this increase happens because of gas migration. So basically, gas starts to migrate, and as it goes upward, the casing pressure starts to increase. After 200 psi, now we know that casing pressure increased by 200 psi. Bottom wall pressure increases by 200 psi. Since we are going to do by 100 psi increments, so we assign 100 psi as a safety factor, and we calculate how much mud we need to bleed or remove from the annulus to basically compensate for 100 psi, meaning that we put 100 psi equals to the amount of mud which can apply 100 psi hydrostatic pressure. Obviously, hydrostatic pressure is calculated by 0.052 times height times density. We know the density of the mud inside the annulus, and we can calculate height. After calculating the height of mud we need to remove, we can convert it to volume. Since we're removing the mud from the surface, then we need to use the cross-sectional area at the surface, which will be between the previous casing, ID of the previous casing, and OD of the drill pipe. So we calculate the cross-sectional area between the previous casing and the drill pipe and multiply that by the height. This gives us mud increment. Uh, so casing pressure increases, let's say hypothetically, for every 100 psi, we need to remove 1 barrels of mud. I'm just throwing the number. So we we start the operation. In this example, for example, casing pressure increases from 500 to 700 psi, and we want to reduce. And we know that since casing pressure increases by 200 psi, bottom pressure also increases by 200 psi, and you want to maintain the bottom pressure constant. Uh, and we want to reduce. How we do that? By reducing the bottom pressure by 100 psi. And how we can reduce the bottom pressure by 100 psi? By removing a certain amount of mud inside the annulus, which basically applies the exact value of 100 psi. So after observing 200 psi increase, we bleed off the mud, and uh, gas expands. So this is gas migrates. Here we basically removing the mud through the choke line, and as we remove the mud at the surface using choke line, gas also expands. And we know the volume of the mud we need to uh, remove. After removing the exact volume of the mud, then we close the choke line, and we let when we close the choke line, what happens? The gas bubble starts to migrate again. So another gas migration happens here by 100 psi. Again, from now, every 100 psi, we have to repeat what I already explained. So we wait, gas expands, and the casing pressure increases from 700 to 800 psi in this case. Now we know that when surface casing pressure increased from 700 to 800, meaning by 100, bottom pressure also uh, increases by 100. So in order to reduce the bottom pressure, again, we bleed off the mud and let the gas expand again. So we are maintaining the casing pressure constant, but we are reducing bottom pressure back to initial value. So we keep doing that till the gas bubble reaches the surface, and then we replace the gas bubble uh, with the current mud. And at that point, the casing pressure goes back to zero. So what you guys are seeing here is basically is the first part of driller's method. So in driller's method, if, as you guys see here, you see a continuous increase. However, when we do volumetric method, this happens, it becomes like this. And then it goes down. So basically, this part becomes like this. Uh, what happens to the hydrostatic pressure inside the annulus? Obviously, since we are removing mud and we are letting the gas expand, there's a substantial difference between the density of the gas and the density of the mud inside the annulus. So as we let the gas expand and we remove the mud from the top, hydrostatic pressure inside the annulus starts to decrease incrementally. As you can see here, uh, when the gas migrates, nothing is changing in terms of the height of the gas column and the height of uh, mud inside the annulus. So hydrostatic pressure remains constant. When we start bleeding off mud, so we are removing mud, which is the heavier fluid, hydrostatic pressure inside the annulus starts to decrease. So hydrostatic pressure inside the annulus starts to decrease. When we close the choke line and we we let the gas migrate, since there is no change inside the annulus, the hydrostatic pressure remains constant. As soon as we reach the pressure increment, which is 100, in this case, it becomes 800, then again, we open the choke line. So we are bleeding off the mud from the surface, and by doing that, gas expands. So hydrostatic pressure inside the annulus decreases again. And this happens till gas reaches the surface. As soon as gas reaches the surface and we start replacing the gas with the current mud, the hydrostatic pressure increases and reaches uh, the original value. Now let's see what happens to the bottom pressure. Uh, both weight and weight method and Dreller's method are constant bottom pressure. And as I mentioned at the beginning of the volumetric method, uh, bottom since the volumetric method is basically similar to the first circulation of Dreller's method, so bottom pressure must be constant. As you can see here, bottom pressure is fairly constant. So bottom pressure increases initially when the gas migrates, because when gas migrates, bottom pressure increases. When we start bleeding off mud and let the gas expand, bottom pressure decreases, because this is the whole point. We are removing or we're reducing bottom pressure by removing the gas, the mud from the surface. Then again, it increases when the gas migrates. It goes down the same value, so it increases by 100. When gas migrates, it drops by 100 when we remove mud column. We remove mud from the surface, and this keeps happening uh, till uh, the formation fluid, which is gas, basically reaches the surface. When the gas reaches the surface, we replace the gas with the mud, then this pressure becomes constant, flat. Uh, Again, just to make sure that everyone remembers from the previous sessions, bottom pressure is always equal to the hydrostatic pressure inside the annulus plus the casing pressure. In order to maintain the bottom hole pressure constant, we have to make sure that this plus this remains constant. Since this is increasing, we have to reduce that. Uh, and casing pressure, as you guys remember from here, it keeps increasing. However, we can calculate the pressure at each point using this formula. Safety factor, let's say 100 psi, plus casing shutting pressure, let's say 500 psi. And this is the number of times we are repeating. And let's say pressure increment, we go with 100 psi pressure increment. At the beginning, casing shutting pressure is 500 psi. So we let the gas migrate 100 psi, and the first iteration will be 1. So 100 psi plus 1 times 100 psi plus 500. So casing pressure at the first expansion will be 700 psi. We bleed off at the surface uh, by 100 psi, so the pressure remains constant at 700 psi. We let the gas expand again, so it will become number 2. So 100, 2 times 200 plus 500 becomes 800. Again, we bleed off mud, so the pressure remains constant. So we keep doing that till gas reaches the surface. The mud increment that we need to bleed off at each interval or at each time we bleed off can be calculated using the pressure increment pi here times annular capacity factor. Annual capacity factor is basically the cross-section area at the surface, which is between casing, the previous casing, and uh, OD of the drill pipe. So pressure increment times ACF divided by 0.052 times mud weight. So mud increment can be calculated using this formula. Let's say if the pressure increment is 100 and you calculate the annual safety factor in barrels per foot, and you know the mud weight, you should be able to calculate the mud increment. And the question I ask here, where does annual ACF need to be calculated? Annual capacity factor, it should be right at the surface because we are removing the mud from the surface. So if formation fluid started entering the wellbore not because of the fast stripping, and we think that we were under balance, and during the static condition we were also under balance, we can calculate the density of kill mods. So we want to replace the gas with the kill mod. So at the end of the operation, we overbalance. We can calculate it using this equation. PF is formation pressure plus safety factors minus 0.052 times TVD minus height of gas times mud weight divided by 0.052 times height of gas. Uh, just to summarize what I already talked about the change in the casing pressure and the volume of the mud we need to bleed off. This table tells us, okay, at the beginning, T sub 1, the casing pressure will be P casing pressure 1, and we remove mud increment. At T sub 2, the time 2, casing pressure increases by pressure increment. So the difference between each two consecutive pressures is equal to pressure increment, all of them. So what happens at the second one, we need to remove two totally times mud increments. So each time, if this basically tells us the cumulative mud increment we need to bleed off uh, in order to maintain the bottom of pressure constant, because I don't know how many times I should emphasize on this point. Well killing operation and also volumetric method, the assumption is constant bottom pressure. So by removing the mud out of the annulus, we are guaranteeing that the bottom pressure remains constant. So by saying that, this is the last slide of well control. Any question? Is there any question, Meyer?
Um, there is just one question.
Okay.
If there is a loss after having a kick, what is the method to apply?
If we have a kick, if you have a loss after having kick,
Yes.
first of all, it's highly unlikely if we have uh, kick and loss, because uh, when kick happens, if we are overbalanced, if we are overbalanced before kick happening, so we should notice the loss circulation. We should take care of that. And if kick does not happen and we are entering an overbalanced pressure formation and the kick happens, so there shouldn't be a loss basically at the surface. I can't think of any scenario that we have kick and then loss. And then if this happened, it will be underground blowout. And frankly, maybe managed pressure drilling is one solution to this problem. So it will not be normal drilling operation, it should be managed pressure drilling. So we have kick
Okay.
and loss. I mean, flow and loss at the same time.
Okay. Another question is, in case we have lost circulation, what can it result to and what can be done to remedy it?
If we have lost circulation during drilling operation, there's
What's the
several.
one?
Pardon me. If we have lost circulation during drilling operation, several techniques can be applied. One of them is to reduce the flow rates. So basically, we're reducing the ECD to minimize or stop lost circulation, or we can pump LCM materials to reduce or cure the loss issue. Uh, or we can go and set cement block. So basically to cure or take care of the loss zone. These are probably three normal procedures can be done during the neck operation when we're dealing with lost circulation zone.
Okay. Another question. In work over operations, no drilling formation. What kill method is recommended?
Usually, what they do is bullheading. I did not cover that here. I did not cover bullheading here because it's in the workover. But it's bullheading, basically pushing the uh, formation fluid into the formation.
Okay. Thank you so much for this informative webinar. And to highlight, this session has been recorded and will be uploaded soon on PyPetro YouTube channel. So make sure to subscribe on our channel. Thank you, Dr. Hussein, again. And thank you all. Stay safe and bye.
You're welcome. Thank you very much.
Bye.
Bye bye.